Alright, so now I'm going to talk about the definition of the Riemannian connection. Or sort of Levi-Civita connection. So this is sometimes referred to as the fundamental theorem of Riemannian geometry. Okay, so I'm going to let sort of these brackets denote the Riemannian metric. Okay, so let's state the theorem due to Levi-Civita. So on a Riemannian manifold, M, okay, there exists a unique affine connection nabla, okay, that satisfies the following properties. First of which is this notion of symmetry, which I talked about before, right? That when you swap the sort of entries, it's like the two vector fields which the affine connection acts upon. It's like and you take the difference, right? Then you end up getting something which is just given by the Jacobi-Lie bracket of those two vector fields. Okay, and then the other one is the following. It's this notion of metric compatibility. Okay. So if you have three vector fields, so the vector field acting on the bracket of, the Riemannian metric applied to those two vector fields, that's equal to the affine connection acting on the first vector plus sort of the bracket. It's like the inner product, if you will. It's like, but with the affine connection acting on the second entry. Okay, so this is metric compatibility. So this is sort of an infinitesimal statement. Another way to sort of think about this is that if you take a pair of vectors and you look at the inner product that's like between those two vectors, and then you parallel transport that pair of vectors by the affine connection, then the inner product between the parallel transported pair of vectors is the same as the inner product of the original pair of vectors. Okay, so so again, there's a sense in which the parallel transport, it's like which the affine connection defines, right, is compatible with the metric. Right, and this has to be true for all vector fields on M. Okay, then this connection, this distinguished connection, so this affine connection is called the Levi-Civita connection. Or the Riemannian connection. right, and it is characterized by the kazoo formula. Okay. All right. So, so what the formula does, of course, is that it shows you how it's like the bracket, sorry, the affine connection acting on some other, it's like vector field, right? It's expressed in terms of things which just involve the inner products, it's like, and the Jacobi-Lie bracket, okay? And so in particular, if you wanted the components of this, it's like you could just have this be, you know, it's like one of the I-coordinate bases, right? So that would give you the components, it's like which you have for this, and then give you what you need. All right. So let's try to use this to actually compute the entries in terms of the Christoffel symbols and the kazoo formula. Okay. All right. Okay. So let me try to erase some of this. I'll just erase up to here maybe. Now. So, since the Riemannian connection is symmetric, you know that that's the Christoffel symbol, so it's like have a symmetry. Okay, and then you can use the kazoo formula. You can show that the sort of Christoffel symbols are related to coefficients of the metric. Sorry, the Christoffel symbols. Of the Riemannian connection. Related to the coefficients of the Riemannian metric. As follows, right? So if you have gamma ijk, this is going to be equal to 1/2 the sum over L of g KL, then partial I g Lj but partial j g Li minus partial L Gij. Okay, so I shouldn't. Okay, so you might ask what the upper and lower has to do here. So where GKL with the upper indices, right, denotes the matrix inverse. Of GKL. Okay, what that means then is that this is to say that the sum over I, right, of GKI, GIL is equal to the quantical delta function, right, delta KL, which is 1 if K equals to L, then 0 otherwise. Right? All right, so in theory, of course, it's like that then allows you to compute the Christoffel symbols. It's like in terms of the metric, it's like coefficients of the Riemannian metric. In practice, of course, we will try to avoid using this actually to compute stuff. Right, so, but anyway, so this is, at least in principle, it's like a formula which you could use to compute the Christoffel symbols of the Levi-Civita connection in terms of the metric coefficients of the Riemannian metric. Okay, so then one final remark is that on Euclidean space, right, this Riemannian connection reduces to the canonical connection. Okay, and if you recall, it's like the canonical connection is what happens. It's like when the Levi-Civita the Christoffel symbols, it's like all vanish, right? So an easy way to see this is that the Christoffel symbols vanish. It's like when the metric is constant, right? Because you have all these sort of directional derivatives. It's like in each of the coordinate directions here, all these entries will be 0. And so, you know, it's like gamma ijk is identically 0 if sort of gij is constant, right? Okay, so, right. And in particular, again, it's like when all the Christoffel symbols vanish, it's like then you're just left with the canonical connection. Okay, all right. So what we're going to see in a little bit is that, you know, in practice, we're going to try to avoid, it's like computing, again, this sort of Levi-Civita connection using sort of the coordinate version of the kazoo formula, right? And we're going to study how to actually characterize, it's like the Levi-Civita connection in the case of embedded manifolds and quotient manifolds in the Riemannian setting. Okay, so let me just stop here for now.